introduce now. We speak about external holomorphic forms from the regular locus of a complex space to a full.
Okay. Is it on now? Okay. So yeah. So thank you very much for the chance to give a talk here to the organizers. I should say that the title is really long, which is kind of unusual. But the cause is that I'm helping to run this seminar for graduate students where we teach them good practices. And one good practice is to use descriptive titles in your papers and talks. Okay, I also want to say in general, so I know it's very late in the afternoon, but still I'd be very happy if you could ask questions, because it's much nicer to give a talk when people ask questions. But, okay, so what I want to do is, I want to revisit a theorem from a couple of years ago, which deals with this problem of extending differential forms. Okay, so let me start by stating the theorem. So this theorem is due to Grape, Quebecus, Kovas, and Peternel. And what it says is that, so let X be a normal algebraic variety with KLT singularities. So this will be normal algebraic variety over C with KLT singularities. And then you take a resolution of singularities. So R from X tilde to X is a resolution. And then you can look at differential forms on the set of regular points and ask whether they extend. And what they showed is that in the setting of KLT singularities, every differential form from the regular points extends to the resolution. So for every algebraic P form on X reg extends to X tilde. To an algebraic P form on X tilde. Okay? In fact, they show this even locally. So this is true even locally in the following sense that, so locally, if I have the inclusion from the regular locus into X, then what you actually show is that the push forward of the sheaf of P forms from the resolution, when you embed it into the forms on the regular locus, that's actually an isomorphism. Okay, so it's even locally in the Zariski topology. Okay. So this, I'm not going to write this down, but this result, this is from 2000, or this was published in 2011, and they have since then actually found a really big number of applications of this theorem. So for example, I think the best known cases of this Zariski-Lippmann problem, like whether local freeness of the tangent sheaf implies non-singularity, that can be done with this kind of theorem. Some uniformization theorems about varieties with trivial first Chern class that are singular are proved using this theorem and so on. So I mean, you're lucky in that Stefan Quebecus is actually going to be here for the program for next week. So if you want to learn about applications of this, you can ask him, for example. So I just want to emphasize the kind of the philosophy behind the statement. So the philosophy was that this statement is about, this is something about the well-behaved nature of singularities of the minimal model program, right, the KLT. So meaning that somehow what makes this work is the fact that singularities of the minimal model program are nice. And in fact, the proof is very minimal model program theoretic. So for example, the technique is something like this, that you first show that the forms extend with some kind of poles on the resolution, and then you show that there's actually no poles. And in the process, you use special properties of this resolution map for KLT singularities. So for example, the fact that when it's KLT, the fibers of the resolution map are rationally chain connected. That's a theorem by Haken-McKernan that goes into the proof. Okay. So, so what I want to do today is I want to consider this problem in general. When do forms extend? And I want to answer it for you. So I'm going to give you a necessary and sufficient condition for a given P form. When does it extend to the resolution in this kind of sense? And in the process, we will see that, in fact, this philosophy is false. So that this problem of extending forms actually turns out to have nothing to do with minimal model program. That's sort of the plan. So, yeah. OK. So, yeah. So, if I may, so this is kind of sad for me, because the reason why I got interested in this problem in the first place is because I wanted to understand, kind of from a Hodge theorist's point of view, what does KLT singularities mean? Yeah. OK. Anyway, so let me show you the example that we looked at. That kind of that gives a hint for why this problem is not so much about MMP singularities. So the example is cones. So I want to describe this example a little bit. So by a cone, I mean something like this, that I have here, say, a projective space, Pn minus 1. And inside of this projective space, I have some smooth projective variety y. And then I take the cone over it. So my singular variety will be the cone over it. So here's the origin in AN. And then I take the cone over this thing. And this is my singular variety x. OK, so x is, well, for convenience, I'll normalize it. So it'll be the normalization of the cone over a smooth y in Pn minus 1. And then there's a natural resolution, like you just blow up the vertex, right? So if you just blow up the vertex, then you get another copy of y. And all of the lines on the cone, they just make a line bundle. So this is the resolution map. And this line bundle is just a copy of OY of minus 1. Right? That's what the resolution looks like. And so in this example, we can analyze what happens. Now, it's a little easier to study if you do it algebraically. So algebraically, what I'm going to do is I'll take y smooth projective of dimension n minus 1. N will always want to be the dimension of the ambient variety. And then I take an ample line bundle, so L ample. So the ample line bundle is the replacement for this very ample line bundle. And then the algebraic model for the cone is just you take the spectrum of the section ring. Right. And like in this example, so this is normal always, and it's kind of a small generalization of this, because I'm not assuming that the line bundle is very ample. And then the resolution is, again, the resolution is the line bundle L inverse. So this, if you want, you can write it in Hartrott notation as it's the relative spectrum over y of the symmetric algebra of L. So, right. And then this comes with a projection map to y. Okay, and then so this is the algebraic model for the cone. Now, right, it maps to the x tilde maps to x, because this graded ring here is just the space of global sections of the structure sheaf here. So in this case, what happens is let's analyze the n forms on x. So n forms on x versus x tilde. Well, I can calculate this on x tilde. So if I use this projection down to y, I can easily calculate the canonical bundle, right? So the canonical bundle of x tilde is, well, it's the pullback of the canonical bundle from y, q upper star, and then times the relative canonical bundle, and that just, because the line bundle is L inverse, that just gives me another copy of L. Okay? And so then I can calculate the sections of the canonical bundle on the resolution, first of all. So this is just the global sections of this one. You push it down by y, you just get this big direct sum. So So this is h naught of y, omega y times L to the m. And m will go from 1 to infinity, right? Because I have this extra L here. And on the other hand, I can calculate the sections on the regular locus, the n forms on the regular locus, right? And I want to compare these two. So the regular locus, by this resolution, is identified with x tilde minus the 0 section. So I'm just calculating the sections of omega x tilde outside of the 0 section. So this is the same thing as h naught x tilde minus the 0 section, omega x tilde. And if you do the calculation, you get the same direct sum except for all m's in z. Like this, okay? Okay, so you see that the condition is all of the n forms extend from the regular locus to the resolution, exactly when those extra terms are not there. So that's exactly when yeah, and then, I mean, by similar, slightly more complicated arguments, you can work out what happens for the forms of lower degree. n-1 forms, n-2 forms, and so on. Just use all the standard exact sequences for the differentials and so on. And you find that, in fact, this condition rules all the other ones. If this single condition holds, in fact, all the forms extend, just by calculation. Okay? So this is just this kind of vanishing condition. Like, the canonical bundle of Y should not have sections, and then L should be positive enough to kill these other section spaces also. But now if I compare this to the KLT condition, KLT is really restrictive. So X is KLT, this cone, this only happens when Y is Fano. And this line bundle L should be equivalent to a positive multiple of minus KY. Okay, so the Fano condition is really restrictive. It's much more restrictive than n forms extending and forms extending. So from this example, you would think that probably it's not so much about MMP. Are there any questions? Okay. Okay, so then let me maybe give you the general setup that I want to consider for this. So I'm going to go from the algebraic setting actually to the analytic setting, because it works more naturally in that setting. So X will be a complex space, which is reduced, and of constant dimension n. Okay, so this would be the global set of assumptions that I need. In fact, the problem is local, so I'll just work in a local setting anyway, right? So what this means concretely, locally, what it means is that I have some open ball in some c to the n, some ball, and then my x is defined inside of this ball by finitely many holomorphic equations. So this is defined by some holomorphic equations. And the conditions I want just is that it's reduced, and the constant dimension is just for the notational convenience. You don't need this, but it becomes more complicated to keep track of the dimension. Okay, so that's why I put it here. And then I'm going to consider a resolution again. So resolution. Without loss of generality, I can take it projective. Right? Because the usual algorithms that give you the resolution, they work by blowing up, by a sequence of blowing ups, and that will make this morphism be projective. Okay, and then the problem is to describe, well, let's first say it like this. So which holomorphic P forms on X reg, the set of smooth points of X, extend to X tilde.
So when you say
yeah.
it's projective without loss of generality, you mean there exists a projective?
There exists one, right. And this question, it turns out to be independent of which specific resolution you use.
Projective resolution?
No, which proper bimeromorphic resolution you use. But just use a projective one because later it will be convenient. But it actually, the answer to the problem actually turns out to be independent of the resolution. Okay, so this is the concrete formulation, right? If you have a form on X reg, it gives a form on some big open set of X tilde, and you can ask whether or not it extends. Like in the theorem, I can say it in sheaf theory terms. So equivalently, I can ask, describe this subsheaf of the forms that extend. So describe the push forward of the forms from the resolution as a subsheaf of the forms on the regular locus. And as I said, this thing here, one can show quite easily by the usual, take two different resolutions, dominate them by a third. By this argument, you can show that this subsheaf is actually independent. So this is independent of the resolution. Okay, so you can pick any resolution for this. Okay, so is the problem clear? Yeah? Okay. So, okay, so before I tell you what the answer is, let's think about this problem a little bit in two specific cases, okay? So one interesting case is the case when P is equal to 0. This is kind of the baby case of this problem. So there it's about holomorphic functions, right? So we're looking at, do holomorphic functions extend from X reg to X tilde? So does someone want to make a guess as to what the condition is for when do the holomorphic functions extend? Normal, yeah, right. So normal is the most common answer, yes. So normal would be the condition if we were trying to extend holomorphic functions from X reg to holomorphic functions on X, right? Then it would be normal. Here we're asking something slightly weaker. We want to extend the functions from X reg to functions on the resolution X tilde, right? So you need something slightly less. In fact, it's just enough if the codimension of the singular set is 2 or bigger, right? So it's just equivalent to. And the reason is basically that this, the push forward of the sheaf of functions from the resolution, these are actually just the functions on the normalization. Okay, so then what we're really asking is, do functions on X reg, which are really functions on a big open set of the normalization, extend over the missing points in the normalization? And the condition for that on the normal space, like the normalization, the condition is just in the set over which you would try to extend needs to have codimension 2 or bigger. Okay, so this is. So for functions, very easy. And then the other case is the N forms. So in the case of the N forms, there's not such a simple answer, but it's somehow connected with rational singularities. So for N forms, I'll remind you that, so it will work if X has rational singularities. So if X has rational sings, which, again, so it means that the push forward of the structure sheaf is the structure sheaf, and the higher direct images are 0. Then all N forms will extend. Right? Because this implies, by the discussion in the other lectures, this implies that the push forward of the sheaf of N forms is actually this first cohomology sheaf of the dualizing complex downstairs. And this guy is always a reflexive sheaf by general principles. So then this gives you the necessary condition for extension. So this is reflexive. And so this implies that all N forms extend. Well, I should say on X reg, extend. To X tilde, okay? So this is one case where it definitely works. Now, if you ask me about the relation between rational singularities, I can vaguely say what the relation is. So you'll remember from the other talks that rational singularities includes, in particular, normal and Cohen-Macaulay as conditions. And if you just ask for extensions of N forms, that's the same thing as taking the rational singularities and just removing normal and Cohen-Macaulay from it. So if you just look at extension of N forms as its condition by itself, it's like rational singularities minus normal and Cohen-Macaulay. So that's sort of that's the answer vaguely. So maybe I can at least write the slogan sort of. So N forms extend in this sense. This is equivalent to, in quotes, without the Cohen-Macaulay condition. No, you actually don't. No, so because again, reflexive and extension are only equivalent on a normal space. If you're not on a normal space, then extension is slightly weaker than reflexive, and that's sort of, yeah. So I can give you, I'm not going to prove this, but I can give you at least the fact. So this in turn, you can write this in a way reminiscent of this one, of this condition, just in terms of supports. So in fact, this N forms extending is equivalent to, when you look at the support of these higher direct images of the structure sheaf, and the codimension goes down. So this is the precise equivalence. Okay, you don't need them to vanish, but you need them to be supported in fairly small sets. Okay, so if you're inclined towards making new definitions, you can go and say, let's define a new class of singularities, weakly rational singularities or quasi-rational singularities or what have you, and you define it by this kind of condition. And then you have a fancy name for N forms extend, if you want. You can do that. Yeah, all right. So Kemp's criterion for rational singularities, or? Yeah, right. We're sort of requiring less so that we're not kind of imposing the Cohen-Macaulay condition at the same time. Yeah. exactly. Are there other questions? Yeah. So this equivalence, it comes from, so it's basically duality. I mean, you can, if I have a complex of sheaf, if I have a sheaf, I can describe whether or not it extends over sets in terms of some support condition on the dual complex. And in the case of the canonical bundle, what happens is, because by Grauert-Riemenschneider there's no higher-diaged images, when I dualize this one, I just get the higher-diaged images of the structure sheaf. And then this condition of extension translates exactly into this sort of vanishing condition there. So it's like a standard kind of complex analysis type calculation, yeah. Okay. Well, yeah. Well, actually, let me. Okay, so and then I'm going to tell you what the answer is in general, and then hopefully I have enough time to tell you at least sort of the main point of the proof. Okay. So maybe I'll state the answer as the theorem. So this is in a joint paper with Quebecos. Yeah, so maybe let me say the notation again. So there is a global statement that you can make. I'll give you the local statement only because it's a little easier to write. Okay, now if you like, I can tell you how to make the global statement. So I'll consider this local situation where, so B is a ball again with coordinates. So I'm going to need the coordinates, that's why. So I have the coordinates Z1, Z2 up to Zn plus C. And again, n is always the dimension of the space I'm interested in. So I'm using the C for the codimension, right? So then X is inside of B is a reduced constant dimension n. And then I pick a resolution. Okay, now my theorem is going to have two parts. So the first part is not due to us, it's really well known. The first part will describe when the n forms extend. This I'm just giving kind of for completeness. And then the main part is the second part where we describe what the other forms do in terms of n forms. Okay, so there's a part A, which is well known, classical if you like. It says that if I have some form alpha, which is an n form, then this extends to x tilde, to the resolution, if and only if, well, so there's an analytic description for the condition, which is basically if it's square integrable. Right? So what you do is you take alpha and wedge it with its conjugate, then you get an nn form. And the nn form can be integrated. And the condition for extension is just that nn form should be integrable locally on x, so including like in neighborhoods of the singular points. Right? So if and only if the nn form alpha wedge alpha bar is locally integrable. On x. Right? So this, I mean, if you pick the resolution nicely to be like a log resolution or something, this just comes down to the fact that if you have a holomorphic function outside of a normal crossing divisor, it will extend holomorphically exactly when it's square integrable. Like the L2 version of Riemann extension, basically. So this is just for completeness. I mean, this is not new, as I said. So part B is the new part. So part B is if I do the same thing for P forms, it'll give me a P form on the set of regular points, then this extends to x tilde if and only if. Okay, and then here's the condition. So I'm going to take alpha, and I'm going to convert it into an n form by just wedging with a bunch of dz's. So I just wedge with enough of the dz's to make an n form. And I do the same thing for d alpha. Again, I wedge with enough of the dz's to make an n form. And if these things no, they're arbitrary. Like in each case, you just take all possible subsets of size n minus p here, all possible subsets of size n minus p minus 1 here. And then for all of these finitely many forms, they should extend as n forms. N minus p. Okay, so that's the condition. So this is actually just a finite set of things that you have to check. Right, so you see in particular that it doesn't mention MMP in any way, right? So it's not really about KLT singularities. Yeah? Is there a way to compare with KLT? Yeah, I mean, right. So basically, KLT contains something like extension of n forms, right? But it contains these other conditions on the canonical class, like Q Cartier, or Q Gorenstein, sorry. So essentially, what you need from the KLT is the extension of n forms bit. But you can throw out stuff like Q Gorenstein or normal or such conditions, right? Yeah. Okay, right. So So I want to talk about the proof, but let's draw some corollaries from this theorem. Okay. So is the statement clear? Oh, okay. Yeah. Yeah. Are there examples? Is there some implication between them? That's a good question. Yeah, so I know some cases where there is an implication between them, where one of them seems to imply the other one, but I couldn't figure out any general implication. In some examples, yes, but I don't know the general principle. Yeah. Okay. So so let me draw some consequences for this. So these consequences are very sort of simple. So one consequence is, just to show it's a nice criterion. So if n forms extend, I claim, so this is kind of our replacement for KLT, right? If all n forms extend, always, then in fact all forms extend. Then p forms extend. Okay, so I'm using this n forms extend as a shorthand for n forms extend from the regular locus to the resolution, right? Okay, right, I mean, this is kind of obvious from this because you see that the only condition that's being imposed on extension is some condition on n forms. So if n forms always extend, there's no condition here, and therefore everything extends, right? Yeah, so this is a sort of nice corollary. Then the second one, so for a long period of time, our understanding of this problem was sort of stuck at this point. And then I gave a talk at Columbia, and then I think Johan de Jong asked me, like, could this same kind of thing be true for other forms? Like, somehow suppose you know that n-1 forms extend. Would it imply that that all lower forms extend? And I said, no, I don't think so. But then I went back home and thought about it. And in fact, the answer is yes. So this 2 is actually, 2 should be credited to Johan. So the statement is that if p forms extend for some p, then the lower ones extend, right? So then also p-1 forms extend. Okay, so you actually have this kind of hierarchy that n forms extend is the strongest condition, then n minus 1 forms extend all the way down to functions extend, which we saw is just this condition on the codimension of the singular locus. Well, I might as well prove something, right? So let's prove this. So let's take alpha p form on xreg. Then you want to check the condition for p minus 1 form. P minus 1 form. You want to check the condition for the extensions. Well, so this condition involves alpha and d alpha being wedged by certain forms like this. But so you see that this condition will be implied by a condition for p forms, because then if I take, for example, d alpha, this will be a p form, and alpha wedge each of these dzis, they are p forms. Right? So they extend, because we're assuming that all p forms extend. And, well, the fact that they extend by b means that if I wedge with the remaining dzis, I get n forms that extend. And then if those n forms extend, again by b in the other direction, that's enough to conclude that alpha itself extends. Okay, so this implies by using b twice that alpha extends. Okay, so you see that this criterion is actually fairly simple to, yeah? It's equivalent for the n forms here. So there's a version of this kind of condition where you ask about the supports of the other omegas, the omega q's. So you can make a version of this kind of definition where instead of pushing forward omega x tilde, you can push forward sheaves of differentials. And then those conditions will imply these kind of extension conditions, but they will not be equivalent in general. Yeah. Are there other questions? No? Okay. Yeah, maybe. Okay, so now I want to give you an idea of the proof. Oh, I want to give an idea of the proof. Is this yellow? So I'm not going to be able to give the whole proof, but at least I think I can give sort of what the main point is. So the idea is, what we use is, instead of MMP techniques, we use Hodge theory in the form of Hodge modules. And then the main thing that makes it work is the decomposition theorem for Hodge modules. Okay, so this is another instance where it's not so obvious beforehand that this is a good thing to do, although then somehow afterwards it does seem pretty obvious that it was a good idea to do it. Right. So maybe I should say a little bit sort of where this comes from. So maybe let me first say, I think everyone knows that Hodge theory is making statements about holomorphic forms, right? So there is an obvious connection between this problem and Hodge theory, because Hodge theory talks about holomorphic forms. So one of the basic kind of statements is that if X is a projective variety, a smooth projective variety, then the space of P forms on X actually injects into the Pth cohomology of X with complex coefficients, right? This is one of the basic statements. And so for the purposes of this problem, I see the role of Hodge modules as letting you do something like this, but not in the case of a single space X, but in the case of a morphism, or in the case of a family. In our particular case, in the case of this resolution morphisms. So Hodge modules kind of let you do this for morphisms. So in particular, we'll be able to have some statements that for our resolution map, and that's how it enters this problem. Okay, so I'm right. So maybe let me first say how I see the P forms in this case, right? So so I'll have the, well, actually let me first set up the notation again. So what's our notation? So we have our X, which is embedded into this ball, and the inclusion, let's call it I. And then we have the resolution from X tilde. And then we'll have the composition that I'll just call F. Okay? One technical aspect of this Hodge module theory is that you use D modules, and D modules really only work, I mean, at least if you're like kind of simple-minded like me, the D modules only work on a non-singular ambient space. Okay? So I'm really not going to work on the singular space X, but I'll work with this embedding, and so that I can work on a complex manifold. Okay? So what we're interested in is I'll remind you, we want to describe this push-forward sheaf. I mean, I want to really describe R lower star omega xp. I might just as well say I want to describe the push-forward sheaf all the way to B, right? Which that's really it's really the sheaf on the singular space pushed forward into this complex manifold. This is our goal. And so the way I see the P forms as someone who works with Hodge modules is the P forms come up if you take the holomorphic de Rham complex and then you take the stupid filtration on it. It's a graded piece for that, right? So the omega P on this smooth variety X tilde, or on this complex manifold X tilde, this appears as, this is a graded piece of the de Rham complex, the holomorphic de Rham complex. If I just do the stupid filtration by degrees, right? This complex is filtered by degrees going to the right, and if I take a suitable subquotient for the filtration, I end up exactly with a single sheaf omega p. So this is how the omega p will enter. And then what the Hodge module stuff will let me do is, it will let me take this description and actually give me a nice description of the push forward by the map. So, okay, so let me say very briefly, so we're going to work with these Hodge modules a little bit. So Hodge modules on a complex manifold Y, for the purposes of this talk, vaguely speaking, what they are is they're like variations of Hodge structure, except that you allow some singularities. So they're variations of Hodge structure, polarized variations of Hodge structure with singularities. So this means things like it can be an actual variation of Hodge structure where it degenerates in some places, or you can have a variation of Hodge structure on some subvariety that you somehow push forward into the whole space and such things. And the way it's implemented is, so concretely, it's a triple like this. So I have a D module, I have a filtration on the D module, and then I have a perverse sheaf. This is the kind of data that we get to work with, okay? So one is M is a regular holonomic D-module. So it's a module over the sheaf of differential operators. For example, in the case of a VHS, it's just a bundle with a flat connection. But when there are singularities, you get an actual non-trivial D-modular structure at the points where the singularities are. And then the second condition is that the filtration is a filtration by coherent subsheaves, by OY coherent sheaves, which is compatible with differentiation. So if I apply a certain differential operator of some order, the index in the filtration goes up by that order. And this is the generalization in this setting with singularities of having a Hodge filtration on a VHS and having Griffiths transversality. And then the third condition is that this K is a constructible, maybe I should write that over here. So 3 is K is constructible with Q coefficients. And if you complexify it, you get the de Rham complex of this M. So if I take K and I tensor the coefficients up to C, then it becomes isomorphic to the de Rham complex of this M. Okay, this is the basic data. This is how they implement it. And then what Saido does is he puts a ton of conditions on these things that cut them down to like really Hodge theoretic objects. And then what he shows is that if you have one of these objects with all of these conditions in place, then in fact it is just semi-simple. It's a direct sum of simple pieces. Each simple piece is obtained from a variation of Hodge structure on some subset by extending it over the singularities and then pushing it forward in the ambient space. Okay, so he gets this really nice structure theorem that says that these gadgets really are just VHS with singularities. But he don't define it that way. He defines it differently so that he has some conditions that you can check. Okay, so the two examples that are relevant for us is, one is sort of the trivial one. So I can just take the structure sheaf with its usual D-module structure, just the defining action by D. The filtration that starts in degree 0, and then just the Q shifted into the negative the dimension of y. This is an example, right? In that case, if I complexify, I get C, and the de Rham complex of the structure sheaf just is a resolution of the constant sheaf C. And then the other example is if I have a singular subvariety, then there's the so-called intersection complex. So I'll write this as a Hodge module on this ambient smooth variety Y. So this I'll write like this. So I'll write the D module as Mx. Again, has some filtration. And then the perverse sheaf is the so-called intersection complex over Q. Okay, so this is some gadget which you take on the set of regular points. You just take this one, just this trivial object, the constant sheaf viewed as a trivial VHS of type 0, 0. And then there's a way to extend it in a minimal way to an object of this category of Hodge modules. This thing exists, but it's not so easy to describe, right? So on the topological side for this intersection complex, there is a concrete kind of description that relates it to intersection homology. But the object itself is not so easy to describe. So the way this is constructed in practice is that you choose a resolution of singularities, you construct the object upstairs, and then you push it down, and then somehow stuff breaks up, and you take the main sum end. So even the construction of this is not very explicit. It's kind of resolution dependent. Okay, but this is like sort of one of the building blocks, one of the basic things that you have on a singular variety. Yeah. You could just work with MFN. I mean, so maybe I should have said this here. So, the reason what this data does is, if you have one of these objects on a projective variety or a projective manifold, then you can take cohomology. So you take the hypercohomology of the de Rham complex, and the filtration will put a filtration on it, and this Purber sheaf with Q coefficients will put a rational structure on it. That's kind of the role that it plays, right? This keeps track of the rational structure, this gadget. You need it in the theory because to talk about hot structures, you want the rational structure, right? Because you want to, but in my specific application, I only care about these two pieces, yeah. Right? Yeah. So maybe, so it's maybe not so fair to burden you with lots of notation late in the talk, but I'll give you one small piece of notation about these de Rham complexes, right? So let me say D is the dimension of Y. So if I have one of these gadgets, I just want to write the de Rham complex once. So the de Rham complex looks much like the holomorphic de Rham complex. Okay, but the indexing works in such a way that this thing lives in negative degrees. So I'm going to write the degrees over it. So the right end, it ends in degree 0. And then the filtration on it, using the compatibility, so you start in degree k, and then each time that each differential in the de Rham complex involves a differential operator of order 1, so that because the filtration is compatible, we'll go up by 1 each time. So we'll go all the way to. And then you can take graded pieces, right? So if you take graded pieces, what you end up getting is, I'll just write it once here, the graded pieces of M with respect to the filtration. And then it just keeps going. And the main point is that these things here, they're only C-linear because you're doing differentiation. But when you take the graded quotients, you actually get a complex of O modules, right? So this is actually a complex of O modules. So yeah, this is. Okay, so now what we're going to do is, so in our setting, we have this map. I start with the constant object upstairs, and its de Rham complex is this holomorphic de Rham complex that will know about the P forms. And then I'm going to push it down by this map. And there the basic theorem is this decomposition theorem. So which in general, so it's, I'll just write the usual letters. So it's Bailenson, Bernstein, Deligne, and Gaber. And then the version for Hodge modules is by Saito. I'll just write it in the specific case. So so it says that the push forward, I'll write it first topologically. So the push forward by this map of the constant guy on the resolution, this breaks up into simple pieces. Okay, and there's a very precise sort of, it breaks up into things that are simple in this category of Purber sheaves. We only care about a splitting in one particular way, namely, we care about kind of picking up the main part that lives on all of X, and then stuff that lives on the boundary. Because anyway, I don't control what the resolution is. So there will always be some junk that just comes from places where the resolution is doing funny things. So what we actually just want is that this will break up into a main piece, which is the intersection complex of this X, viewed as an object on B, and then direct some other things. Other terms that live on the singular set. Okay? This is kind of the version of the decomposition theorem that we need. When you push it forward, it's not a random thing, but the part that lives on X sort of breaks out as a direct summand. And I could write this in terms of the Dram complex. So if I complexify it, this will say that the push forward of the Dram complex of OX tilde is just a complexification of this. This will give me the corresponding Dram complex downstairs of this intersection complex guy, again, plus other stuff. Right? This is how it'll break up. So this is just sort of the topological formulation. And now the point that is really relevant for us is, because we're interested in the forms, and the forms have to do with the filtration on this complex and the associated graded. So what actually, the crucial point is that when Saito proves this, he proves it for these Hodge modules, and in a way that's compatible with filtrations and taking graded quotients of filtrations. So in Saito's version, you can now pass to the associated graded here. So Saito's version will, this works with the filtration. Maybe I should say this here. So in particular, what will happen is, if I take associated graded, so I'll have that the push forward of, so I'll write it, but I mean the exact numbers don't matter. So I can take the graded quotient for the filtration upstairs in the degree minus p. And this, if you translate it, this turns out to be exactly just the push forward of the p forms from upstairs, placed in degree, shifted by this n minus p. And then here's sort of the crucial point, that this thing is compatible with this decomposition. So that on the right-hand side, it also, even on the coherent level, it breaks up into the graded piece of the Dram complex downstairs, plus some other stuff that I'll call R minus P, where R minus P is some unknown complex supported on X-sync. Okay, this is the crucial point. Now I write this as just a single line, right? I mean, it all comes down to just having this isomorphism that you can commute the two things. Of course, that's where all the work in Saito's paper, right? These three exclamation marks. So this is the non-trivial part. Okay, and so now what happens is, if I just want the p forms, I just take cohomology in the right degree, right? So now the push forward of the p forms, this is here, take cohomology in degree p minus n, I guess. Then on this side, you just pick out this. So this will be the cohomology in degree p minus n of this guy, whatever that is. Of m, this mx, plus the cohomology in degree p minus n of this r minus p. Okay, and then this thing lives on X-sync, but this is the push forward of a torsion-free sheaf. So this guy is torsion-free. It's actually locally free on, so this has no torsion. Right, because I'm pushing forward a vector bundle from upstairs. So actually, this guy here, this sheaf that lives on this subset X-sync, it cannot occur as a subsheaf here. Because if this thing was a subsheaf, then the pullback of it would be a subsheaf of this vector bundle, and I cannot have a torsion subsheaf of a vector bundle. So this thing's actually out. And so you see that my push forward of the forms now gets interpreted as, in terms of this intersection complex module. Okay, and so now Now I'll just give you the. I'm about to violate my own principles. Now I just stop. Sorry. So then at this point, this is kind of the main point, right? So now you have to do some translation, translate this isomorphism using the formulas for the drum complex. You can translate this isomorphism into the concrete statement that I gave earlier, that everything is somehow governed by n-forms. Okay, so there's about a page of translation to be done, but it's just bookkeeping basically. Okay, so thank you.
Any questions? Maybe ask a question.
Okay.
So do versus when p is equal to 1, is there any more explicit way of understanding the condition?
I don't know of any, I'm afraid. So you're right that somehow p equals 1 is a really interesting case. For example, for this Zariski-Lippmann problem, right? I don't know a good way of formulating it, even in the case p equals 1. I don't know like a simpler way of saying it except going up to n forms. Yeah.